Yes, class. Am I audible to all of you?
Yes, ma'am.
All right. So in the last class, we had started with the parallel plate capacitors, and we had seen that if battery is disconnected or if the battery gets connected, then what are the changes that will occur? So first thing that we had discussed was the general case. If we have a parallel plate capacitor and capacitance is present, so it is epsilon naught A by D, charge is C naught V naught, potential difference is V naught, and E naught is equal to V naught by D. It's the electric field which is present. Now, if battery is connected, means the battery remains connected and a dielectric constant is filling up the space. Then we say the capacitance, this capacitance which is present, this is K times the capacitance in air. So this becomes K times the C naught, that is the capacitance in air. Then we have charge. Charge also increases because the capacitance is increasing. So the charge also increases K times. So both of these increase. Then we have the potential difference. So potential difference remains constant. So potential difference remains constant when the battery is connected, and if the battery gets disconnected, then it is the charge that remains constant. These are the two quantities which you have to remember. Otherwise, rest of it you'll be able to manage. So potential difference remains constant, and since the potential difference and electric field, they are directly proportional to each other, so we say that the electric field also remains constant. Fine, class. Now next we have is if the battery is disconnected. If the battery is disconnected and again the space is filled up with a dielectric only, then we say C dash, that is the capacitance, it will increase epsilon naught time, K times. Whatever is the dielectric constant's value, it will increase its number of time. Then we have the charge. Now the charge will remain constant. Fine, here the charge will be remaining constant. This is one of the quantities that will be remaining constant, and potential is one of the quantities that will remain constant when we are talking about the battery getting connected. Fine. So this is charge getting remaining constant. Then potential difference decreases by K times because it gets divided by K. So this becomes 1 by K times the charge which is present. Fine. Then we have the electric field. Electric field is again depending upon the potential difference. So since your potential difference is getting divided by K, that it is becoming K times, right? This potential difference, this is becoming K times. So we say if it is becoming K times, then electric field will also become K times, right? The electric field will also become K times. So these are the things which you have to remember, especially from the examination perspective and the numericals, because the questions we have practiced, these are direct, but their applications can be different depending upon this. Now, let us come to the last portion which is left, the series and parallel combination of the capacitors, which was left to be discussed in the last class, and I want to complete it today. A major portion, so at least you are able to understand, because we'll be doing it in a manner that resistance portion is also clear. See, the rules for drawing a circuit which is having a combination of resistor or a combination of inductor or a combination of capacitors, these are truly the same. The basics that we'll be doing, these basics are definitely going to be the same. So we have to focus how do we see the basics of it. Fine. So when we are talking about it, let us start with this. Just a second. Yes, class. Let's come to the portion. Now, see, class, when we are talking about the division of charges, so here one thing you have to remember that how the charges are going to divide, and secondly, you have to remember how the voltage is going to divide. These are the two things which you have to keep in mind whenever you are having the topic of division of charge, because whatever you are studying here in terms of charge, that will be exactly the same when you will be studying about the current in terms of resistor. So see, when you are talking about the division of charge, remember charge does not divide due to any barrier which is coming. Like if we are talking about, let's say a capacitor is coming in between. So charge would not divide because of that. Fine. How the charges will be dividing, that depends upon the branching. If a branching is there, then we say the charges will divide. So look at this example first. Suppose this is a branch, straight wire. A charge is flowing here, Q. So in this segment also, the charge will remain Q only. Right? Now let's say I have bent this wire in this form. And Q was coming. Q charge was coming. So here also at this point also the charge will be still Q. Here, the entire Q charge as it is has traveled. So this division is the division of charge, which is exactly the charge which was present in the starting. Fine, charge will not divide because of any bending of wire or such case. If the charge is coming, it will be having its original value. Now, if I give you this example, look, suppose this is a capacitor which is present. It's coming here. One more capacitor is present like this. Now, here in our example, we were taking charge Q, which was coming. So capital Q is coming. So even on crossing this capacitor, the charges won't be divided over here. The charges would not be divided over here. Here also this will be having charge Q. Here also this will be having charge Q only. Fine. Whatever charge has come in the beginning, now the charge will remain the same as it is. Because of this device, there won't be any obstruction which will be present. But charge divides due to branching. Suppose this was coming. Here at this point, a branch has been made from the same wire. From the same wire. Then we say the charges can divide themselves. Charges have the ability to divide only when branching comes. So when I say this capital Q was coming, look here, capital Q charge was coming from this point A. C1 was the capacitor that came on the way. Nothing happened. Whatever charge was present on the first plate, after getting induced, it is the same amount of charge which is coming here. Fine. Now at B point, a branching is coming. If you see here, see the same wire has been branched into two parts. So if two parts the branching has occurred, this is not necessary that the branching the division of charge will occur equally only. There is no condition like this. The charges can get unequally distributed. If a 5 coulomb of charge is coming, it's not necessary that it will be divided like 2.5 coulombs and 2.5 coulombs. No. When we say a charge is coming, it can happen that 2.5 coulomb is also getting divided, and it can also happen that 3 coulomb is being received in one branch and 2 coulomb is being received in one branch. That is also valid. Fine. So charges have divided, and now it's no more capital Q. Though when you add Q1 and Q2, you will get capital Q back because it's actually the division and variation that has begun. Right? It's actually the division and the variation which has begun. So when we are having this capital Q, it is divided into Q1 and Q2. Now see Q1 in the same branch, it is moving. So it is still Q1. Capacitor came, it is still Q1. Regarding this second one, when the charge came, this became Q2. And when this capacitor came, C3, it again became Q2. So only the charges have divided here where branching is present. This is one thing which you have to remember. Secondly, what happens to the voltages? See, voltages do not divide potential. And see, one more thing, class. Whatever you studied about the charge, same condition is valid for the current also, but that we'll discuss when we'll be discussing current electricity. So right now when we are talking about the division of the voltages, so voltage will be divided exactly due to a barrier which is present. Like see, if I have a charge, suppose this is a wire coming and there was a voltage present in the wire initially, fine, and this is a straight wire, fine. Now what would be the voltage at this point? V, voltage is still V because it's a straight wire, nothing difficult over here. But when I have put a capacitor here or a resistor here, suppose resistors and capacitors have been put. If the potential here is VA, it would be here VB. And if here it is VB in the same branch, here it will be VC. Because potential divides due to a barrier, that is your devices. Devices break up the voltage. So voltages do change. And if there is branching done, there is no effect on this voltage. If the voltage here was V, here also it will be V, here also it will be. No difference in the branches. Fine. These are the differences that come. And bending affects nothing. Bending of wire affects nothing. Neither the charges nor the potential. So here it was V, here also it will remain V. So these are some things which you should remember. Like look at this example. VA was the potential that was coming from point A. Now what is happening? Because of the capacitor C1, right? Potential has changed. It was VA on the left hand side of the capacitor. Now on the right hand side, it is VB. So VB will be continued till here. Branching has occurred. Nothing occurs. Nothing happens due to branching. Even if branching comes, this gets divided. Same potential will be there. Same potential will be there. But as soon as the device is there, potential changes. VC. And look here, VB was coming, device came, so it became VD. Why are we studying this? Because you have to identify some circuits. You will not be able to identify whether they are of series combination or parallel combination. So there are certain techniques to remember these on the basis of potential and charge. If charges remain same, we say it's a series combination. If potentials remain same, we say it's a parallel combination. So in the circuits where you are not able to identify by looking at the circuit, whether it's a series combination or a parallel combination, what would you do in that case? You will check the potential. If the potential is same in the wires, you will directly conclude that this is a parallel combination. If you have seen and all the charges are remaining same, potentials are changing, so you will conclude the fact that this is a series combination. So it is helpful. That's why you should know these basics. And this is valid for all the circuits of AC also, whether these are inductor-based circuits, resistor-based circuits, or your capacitor-based circuits. First write it, then we'll start with the series combination. Just write it till here. Let us look at the series and parallel combinations class of capacitors we are talking about now. So these were the basic rules which you have to remain see. Now see, when we are talking about the capacitors, in series combination, charge will always remain the same. Suppose this is a first capacitor. This is a second capacitor. Third, fourth, fifth, sixth, and nth number of capacitors are connected to the battery with voltage V. And see, charge remains constant. So we have the same charge. So when we talk about the first charge, it would be CV. So C1V. C1V1. We are talking about one single capacitor. Let's talk about the second capacitor. It is C2V2. Third capacitor, it's C3V3. But we know all these charges, Q1 is equal to Q2 is equal to Q3. So what we can do, if I write what is the net charge, I can say it is Q1 plus Q2 up till Qnth, right class? Now see class, when I write the total charge, this is same. Now let me do one thing. Let me write the total potential which is present. Fine. From here, this is the formula which is present. Now let me do one thing. Let me remove this 1, 2, 3 so that you remember that all these charges are at least same. Now if I write total net potential, what would it be? V1 plus V2 plus V3 up till nth, Vnth. Now what is the value of V1? V1 is equal to Q by C1 plus. What is V2? It is Q by C2. What is V3? Q by C3. Up till Q by Cnth. And what is this net voltage? Net voltage is the net charge by the net capacitance, right? Look, charges are getting cancelled from everywhere because these charges are same. What are we left with? 1 by net charge or equivalent capacitance. It is 1 by C1 plus 1 by C2 up till 1 by Cnth depending upon the number of capacitors if n number of capacitors are connected. So in series combination, how do you solve the capacitors? You reciprocally add all the capacitors. Fine. Reciprocal addition of all the capacitors is done. So 1 by C net, this becomes 1 by C1 plus 1 by C2 plus 1 by C3. If 3 capacitors are there, if 4 are there, so 1 by C1 plus 1 by C2 plus 1 by C3 plus 1 by C4. Nth are there, so just keep on adding whatever is the number of it. Wait. Now look. So total charge of the entire circuit, this is the total charge. Total charge will be the total capacitance, which is the equivalent capacitance by the total voltage. Fine. Now, suppose if a question comes to tell the individual voltages of the capacitors which are mentioned. Suppose you have to tell the individual voltage. So what will you do? Q by C1, Q by C2, with which method we have calculated. Suppose individual capacitance. So C1 is equal to Q by V1, right? Like this also you can use the formula. But what about the charge? Charges would be the same in all of them. Now let's come to energy. So total energy would be, this is the total energy, half C equivalent V square or half Q square by 2C equivalent. Now individual, suppose if a capacitor is, one capacitor is there, C1, V1 having Q amount of charge flowing. Then you will say half C1, V1 square energy. For the second one, half C2, V2 square. Or in terms of the second formula which we have studied, you can use Q square by 2C1, Q square by 2C2. Like this, all the values you can use. We'll see some more values we'll see. First, write this down. See, class, here you have to calculate the C equivalent. So you have the two values of capacitance. Two capacitors are present. It's a very easy question to start with. C1 is equal to 5 farad and C2 is equal to 10 farad. Fine. Now a charge will be flowing. And see, the same charge is flowing. This is a series capacitor because this does not affect our charge. And the potential of the circuit, this is 10 volts. This must be having its own potential also, V1, V2, that we'll be calculating soon. So first part is C equivalent. So we have studied that C equivalent for the series connection is 1 by C1 plus 1 by C2. So 1 by C equivalent, this will be 1 by 5 plus 1 by 10. So this gets multiplied and divided by 2. LCM is 10. So this becomes 1 by C equivalent. This becomes 2 plus 1, 3. Now C class, whenever you're solving this type of question, be careful to reciprocate it. Many of the students leave their answer at this step. No class, this is our 1 by C equivalent. We require C equivalent only. That is 10 by 3 farad. So this would be our answer for the first part. Fine. Now second part. Total voltage across the circuit. Total voltage across the circuit is given. These are the individual voltages. No, total voltage across the circuit, this is mentioned. So this is the answer for the first part. Second part, see, total voltage, this is given as 10 volt, right? Now come to the third part, class. Total charge stored. Now total capacitance is this. Total voltage is this. So can we not calculate the total charge? Total charge is total capacitance multiplied to total potential. So this is 10 by 3 multiplied to 10. This becomes 100 by 3 coulomb. Now, fourth part says charge stored in each. Now see class, this is a series combination. Charge stored in each of these will be the same, whatever is will be same as that of this total charge. So what are the individual charges? Individual charges that are Q1, it will be equal to Q2, which will be equal to the total charge. And this is equal to 100 by 3 coulomb. And this, why? Reason, because this is connected in series combination. Last part, I think, fifth, yes, voltage across each. You have to calculate the voltage across each. See, V1 will be Q by C1. Charge is 100 by 3. First capacitance is 5. So this becomes 20 by 3 volt. And second potential would be Q by C2. So this is 100 by 3 into 10 was the second one, which is equal to 10 by 3. Now, how do I know that whatever I have solved is correct? What potential portion, this is right. Charge, I can figure it out by looking at the values. But how do I know that this part is correct? So see, if I add these two, 20 by 3 plus 10 by 3, I get 30 divided by 3, which is equal to 10 volt. And 10 volt was the total voltage. So the voltage divided as 20 by 3 in 1 and 10 by 3 in second. So as to get the total voltage as 10. All right, class. So this is how you have to solve all the circuits. Write down the question. Some of you have not written the question. Write it. Yes, class. Now let's see the parallel combination. So in parallel combination, voltage remains constant and the charges divide. Why? Because branching comes. Whenever you see branching, it's a parallel combination condition usually. So here the voltages across will be the same. Whatever voltage is the total voltage of the circuit, it will be across through individual wires. But charges would divide. Fine. So here, what is the net charge? If we are calculating the net charge, this will be Q1 plus Q2 up till Qnth. So Q is equal to CV. Just a second. So when we are writing the individual capacitance, this will be C equivalent into potential. This will be C1 into V because potential is not changing. C2 into V up till C nth into V. So voltages will get cancelled this time. So C equivalent in parallel combination. Algebraic addition of all the capacitance which are present. This is the formula. Fine class, now everything will be similar to this. Charge and energy and everything. Now you can calculate. We've already discussed this here. So it would be same. It's just that parallel combination. Let us see a question also based on this. First, write down this. Now class, again, this is also a basic circuit. So after this circuit, we'll be discussing now good type of questions, but at least this should be able, you should be able to solve it. At least tell me the answers one by one in the chat column of all these. This is very easy class. Till now, the first part only Yaya could only answer. How is this possible, class? 5 is this, 10 is this. In series, in parallel combination, you just add them. So 10 plus 5, 15. First part should have been answered by all of you. C equivalent is C1 plus C2, which is 5 plus 10, which is equal to 15 farad. What is the total voltage of the circuit? Total voltage is clearly visible. It is given in the question. It is 10. If you're not able to solve these type of questions, how will you be able to manage infinite circuits and Wheatstone bridge combinations? Total voltage here, it's clearly given. This question has the pattern of a simple formula, like the previous question we have seen. Then total charge. Now, total capacitance is present. Total potential is present. Can't we calculate the total charge? See, total charge would be C equivalent into total voltage. Total voltage into total capacitance. That is 15 into 10, which is equal to 150 coulomb. Next, fourth is voltage across each. Now you require the voltage across each of these. So see, if total voltage is given, so V1 would be equal to V2 here, because this is a parallel combination. So here your answer will still be equal to 10 volt only. Simple paths are given. Fifth says charge in each. Now charge won't be the same. Charge would be different. Q1 will be equal to C1 into V. So see, this will be when you are calculating the total charge. This is, how much is the capacitance given? 5 into, this is 10. This is given as 50. And Q2, this is C2 into V. This is 10 into 10. So this is 100. Now see, if you add the charges, this gives you total charge, which was 150. That was divided. Fifth ho gaya. Sixth is energy in each. See, when we are calculating the energy stored in each. So energy will also be the same, half C1 V square. Here it would be half C2 V square, not V1 and V2, because potentials are same here. So see, this is half C1 is 5 V square. This was 10. So this becomes 100. So 500 by 2, 250 joules. U1. What about U2? Half into 10 into 100. 1000 by 2, 500 joules U2. Fine. Last part. Last part is saying total energy stored. Class, there are two methods by which you can solve. One is directly you can add U1 plus U2. You know the individual charges 250 plus 500, with this is equal to 750 joules. Directly you know. Right, class? Otherwise, you can use half C equivalent into V square. Same answer you will get, class. 750, 1500 divided by 2, that would be 750. Same answer you will get. Solve it now. We will see some better circuits which will involve combinations of series and parallel. Write it, class, and please start answering in the class. Done, class?
Yes, ma'am.
Yes, ma'am.
Ma'am, do we use the value of mu here as 10 to the power minus 6?
Yes, Yaya?
Do we use the power of mu as 10 to the power minus 6? 10 to the power minus 6?
This you are getting the C equivalent.
No, no, I'm just asking that. What do we use? 5 into 10 to the power minus 6.
Minus 6.
As
Yes,
the,
for micro.
yes, ma'am.
Yes, yes, 10 to the power minus 6. But yeah, yeah, no need to solve it. No need to write it because see, you can leave your answer in C equivalent in terms of microfarad, whatever you will get. Right? So don't solve when everything is given in the same unit. You can leave it in microfarad, you will get your answer in microfarad. Don't waste time over there. Do what? See whatever resultant you can get because this is a combination. It's a very easy combination though. At least all of you should answer in this part. Tell me the answers in the chat column. Okay, yeah, yeah, and everyone, please do not solve it in terms of micro. It will become a very lengthy process. At the end, if you require, once you get C equivalent as microfarad, then you can finally write your answer as whatever into 10 to the power minus 6. Okay, class. See, firstly, let us solve this part, class. Look at this. They both are in parallel connection, right? And if they both are in parallel connection, so C12, let's say, this is C1 plus C2 simply. That makes it 5 plus 10, which is equal to 15 farad. You have solved this part, right, class? This you have already solved right now. Now, what are you left with? If these two have been solved and they are giving a common circuit as 15 microfarad, this is now the resultant. See, 10 microfarad with 15 microfarad. Now you look at these two. What are these two? These two are now connected in series, right? These are now connected in series. So final C equivalent, this will be 1 by C equivalent. This will be 1 by 10 plus 1 by 15. So this becomes 150. And here we have 15 plus 10. This is equal to 1 by C equivalent. Right, class? This is still the 1 by C equivalent, which is equal to 25 divided by 150. Now, our C equivalent will be 150 divided by 25. Why? Because you have to exchange it. Understood? Why do you have to exchange it?
Yes,
So
ma'am.
this is
Because it was a
25
reciprocal.
and this. Yes, because it is 1 by C equivalent. So this is 5, this is 30. So 6 microfarad. Did anyone get this answer? Yeah, Yahya has got it. Very good. Write it down. This is the method you have to solve, class. Write it. See, how will you solve this question? First, you will start from here. This is C, this is C. Both are connected in parallel. See, this is 1, 2, 3, 4, 5, and 6. And whenever you have these open ends, it means there's a battery connected. Now your circuit is completed, right? So once you will solve these two, both of these are connected in parallel 1 and 2. So what will happen when two capacitors are connected in parallel? You just add them. So C12 will be equal to C1 plus C2, which is equal to C plus C, which is equal to 2C. So this is now 2C. Fine. Now what can we do? They are also connected in series. They are connected in series now. They were connected in parallel. See, 1 and 2 were connected in parallel. But now 3 with 1, 2, they are connected in series, right? These two are connected in series. So your C12 and C3, they are now connected in series. So 1 by C123, this will be equal to 1 by C plus 1 by 2C. Why? Because C3 is C, but C12 is 2C. So this becomes 2C, 3 by 2C. So your C123 will be equal to 2C by 3. So now look, instead of these two, I can replace it with one capacitor, which is C123. Now how can I solve it? C123 with 4. This is again forming parallel combination. So C123 and C4. They are forming parallel combination. What is 4? 4 is C. What is C123? It's 2C by 3. So C1234. This will be 4 plus 2C by 3. So this becomes, no, not 4, C, sorry. This is C. So this becomes 3 plus 2C, 5C by 3. Right? So I can replace these two and replace it with one single C1234 like this. Now last three, all these three, C1234, C5 and C6, all these are connected in series. That will give us our final answer. This is how step by step you have to move. So 1 by C equivalent final will be 3 by 5C plus 1 by C plus 1 by C. Why 3 by 5C? Because we write 1 by C1234, right? 1 by C we write reciprocal. So LCM is 5C. This becomes 3 plus 5 plus 5. So this is 13 by 5C. But this is not my answer. C equivalent will be 5C by 13. Tell me, class, is this question clear to all of you? Khadija, Yahya, Zaina?
Yes, ma'am.
Yes, ma'am.
All right, good. Right.